Hello students of statics, this is Dr. Dan Baker, and in today's video we are going to take a look at dot products. Now dot products are one of two different ways that we can, quote, multiply vectors. Okay, there is no actual vector multiplication. We either take dot products or we take cross products. And hopefully you've been exposed to these in physics, in previous math classes and different things. But dot products, their fundamental use is to find the amount of one vector which is along another vector. Okay, so dot products, let me write that out here, find amount of one vector along another. Okay, so along another is also saying parallel to another vector. And so if we have a couple of vectors, let's say we have vector A and vector B. Now, if we're going to take a dot product of these vectors, it's useful to actually move them tail to tail. Okay, so let me go ahead and move these guys here. I'm going to put them here tail to tail. And then we can also measure this angle between them, call it angle theta. So we can write out that A dotted with B, so that's the basically notation for our dot product. And the uses, so this is a dot product, and we can use it either one to find the components of A along B. We also can use it to find the angle, find theta between A and B. Now, finding that angle theta can be trivial if we have a two-dimensional problem, but especially on 3D problems, finding that angle can be quite complex. And so it's a useful tool for that. So our most fundamental definition of a dot product is that A vector dot B vector always will give us the magnitude of A times the magnitude of B times the cosine of that angle theta between them. Okay, so recognize that if you dot two vectors, you end up with a scalar value. And that is true no matter what vectors you dot, that they will always give you a scalar. A few properties of dot products is that dot products are what's called commutative. And what that means is it doesn't matter the order in which you dot them. So A dot B is the same thing as B dot A. We know that addition is commutative, subtraction is not commutative, right? That the order matters in subtraction, but it doesn't matter in addition. Another property is that they're associative. And what that means is it doesn't matter whether you associate, say, a constant value A. We're going to take that times A dotted with B, both those vectors. This would also be equal to this scalar constant value times vector A dotted with B, or would also equal vector A dotted with scalar value little a times vector B. Okay, really, it's like if we're going to multiply a constant value, we can multiply before the dot product, after the dot product, it doesn't matter. And the last property is that they're distributive. And what that means is if we have A dotted with the sum of two vectors, B plus C, you could either add B plus C first, or you could take and dot A times both B plus C, or B and C individually, and you'd get the same value either way. Okay, so that's the distributive property. So let's now take a look a little bit more like what they mean spatially. Okay, so if we have vector A, and here is vector B. And we know that from the equation, A dotted with B is equal to, I'm going to rearrange this just a touch. So instead of putting A times B, I'm going to put B times A cosine of theta. Okay, so B we're going to use red, and A cosine theta we're going to use blue. Okay, so if we know that the dot product projects one vector onto another, we could show, and from right triangle trig, it should be fairly obvious, that this distance, right, adjacent to this angle theta, if A is the hypotenuse, we could label this as our A cosine of theta, right? That's the scalar component of A that's along B. And then B itself, right, is this full distance B, all the way from the tail to the tip of B. And so when we take a dot product, we end up with not only the scalar component of one vector along the other, but we also end up with the full length of the vector we're projecting onto. Okay, so introducing a little bit of math notation here, you might have seen before, it's hard to say, but if we're talking about the component of A onto B, okay, and so this in words would be the scalar component of A along B, this is equal to either that A cosine of theta, or if we want to use the dot product, what we can do here is that we can take A dotted with B and divide this by the length of B, right? If we want to divide off that red total length. Now, keep in mind that we've looked at a formulation like this before, that if you have a full vector divided by its magnitude, what does that always equal? Let's see if you can answer that. So vector B divided by length B gives us a unit vector. So we could actually take the full vector A dotted with the unit vector B hat. Okay, so that would give me the scalar component of A that is along B. Now, noting that the scalar component can be either positive or negative. Okay, it will be positive if theta is less than 90 degrees. Okay, in spatial terms, that's basically saying that A and B are generally going in the same direction. So as drawn, this would give us a positive value of the scalar component of A along B. And it'd be negative if theta was greater than 90 degrees. And so what that would look like is if we had, here's B, and if A was reaching back in this direction, then this angle here, which is still theta, is going to be greater than 90 degrees. And so this would be the case where we'd end up with a negative scalar component of A along B. So while a dot product always gives you a scalar, keep in mind that a scalar can be negative. Okay, and that negative value carries with it information that these two vectors are going generally in opposite directions as opposed to generally in the same direction. Okay, so if we want to, instead of a scalar value, a scalar magnitude, we want the vector projection. Okay, so if we want the vector projection, we can write that as PROJ of still A along B, so B is like a subscript. Then this is going to be equal to that magnitude that we just found, right, the scalar component, and we need to multiply it in the direction of B. What term do we have that is pure direction of B? Turns out that term is a unit vector, and so we can write this as A dotted with B hat times B hat. Right, so this gives us the scalar component of A along B, and then multiplying it in the direction of B turns this back into a vector, and we end up with the vector projection of A along B. So some problems might ask you for just the scalar value or scalar component, others for the vector projection. You just have to pay attention to that. And if you do need the vector projection, go ahead and multiply it times that unit vector. Now you'll see in your textbook, and you probably saw it in calculus, there's a much more complicated equation if you wanted to use it for the vector projection. But I think using this unit vector form is just the way to go, as opposed to the other one. I could write the other one out here. It's equal to A vector dotted with B vector divided by the length of B squared times B vector. So basically hidden inside of both of these B vectors and that B squared are two different unit vectors, B. Okay, so if you just start with the unit vectors, use that in your original dot product, multiply times your unit vector, and you're into a vector projection of A along B. Now let's take a look at what happens when we take the dot products of vector components, specifically the unit vectors I hat, j hat, and k hat. So vector dot product of unit vectors. All right, so if we go with the standard XY coordinate system, which then also hold the unit vectors j hat in the y and I hat in the z, and of course I could add onto here my k hat in the z direction. So if I go ahead and dot I hat dotted with I hat, right? Remember that a unit vector is looking for how much of one vector is parallel to another. This is going to equal the magnitude of I hat, which is 1, times the magnitude of I hat, which is 1, times the cosine of the angle between them. So the cosine of 0 also happens to be 1. So 1 times 1 times 1 is 1. Okay, so 100% of I hat is in the direction of I hat. If we then look at I hat dotted with j hat, then we have I hat, magnitude, the magnitude here of j hat, both of those are 1. And now we have the cosine of 90 degrees, right? Because it's perpendicular between I hat and j hat. And so given this angle of 90 degrees, the cosine of 90 turns out to be 0. So what that tells us is none of I hat is in the direction of j hat. And I think that we probably all know that. So let's now take a look at all these different combinations. So we have that I hat dotted with I hat was equal to 1. I hat dotted with j hat is equal to 0. I hat dotted with k hat is equal to 0, because they're also perpendicular. I hat, let's see, actually we'll go with j hats leading this line here. J hat dotted with I hat equal to 0, j hat dotted with j hat equal to 1, and then j hat dotted with k hat also equal to 0 because they're perpendicular. Last row here leading with k hats, k hat dotted with I hat equal to 0, k hat dotted with j hat also equal to 0, and then k hat dotted with k hat is equal to 1. Okay, so what we can recognize is that the only terms that are non-zero are the parallel components. Okay, so what that tells us is if we take in component form and we dot A and B, we're going to get the sum product. If you use Excel much, you might have used the sum product function. So the sum product of the like terms. Okay, so what that means is AX times BX plus AY times BY plus AZ times BZ. Okay, because all of the other terms are going to be 0. And we also know that this is equal to that length of A times the length of B times the cosine of the angle between them. And so this gives you kind of three different terms, and fundamentally the one over here on the left doesn't operate much, but the two on the right are kind of mathematical equations. So say that you needed to solve for this angle theta, you would find the length of both vectors, the components of both vectors, and then back solve for that theta. Hopefully this provides a good, concise introduction to dot products and that you're having a great day.